Thank you. Hope you can hear me okay. So I mainly work in the Helsinki University of Technology, which is called Aalto University now because of some merging business with the business school, who did not want to be called Technology University. So it's just the Helsinki University of Technology. And until today, I also work in Bonn, like part-time. And from tomorrow, I will work in Cologne. So tiny switch. But this is just like a visiting professor's thing, so I'm mostly in Finland. But that's me. I'm really happy to be here. So I was in the online version. Yes, so it's changing in the new year. Yeah. So I wasn't sure what to put here. So I was actually in this online WIMP a few years ago. It was supposed to be in PIMS, I think, but it was in the pandemic time. And I'm really happy to be first time live, because there was one edition in Geneva where I used to work at the time, but somehow I was away. So I'm super happy to be here and it's very nice. So thank you so much for inviting me. So I was a little bit not sure what kind of backgrounds people have here, because I think most people are maybe more inclined to some geometry kind of things, and not so much probability things. So there's not too much content in my talk, don't worry. What I want to say is how these probability things, these random curves that people are interested in, how they are actually very inherently related to conformal field theory. And I think many of us agree that we are interested in conformal field theory or other field theories. And this is in 2 dimensions, because I'm a mathematician, so I can only do simple things. So I listed some kind of outline thing here first. So the slides are having a lot of content, but you don't have to remember. So I just put keywords in case you're familiar, so it rings a bell. So the original motivation for these random curves is coming from statistical physics. So you see a couple of pictures here. This is the Ising model. I give you a definition soon. And this is something called uniform spanning tree. So it's a uniformly chosen spanning tree in some graph, and then some branches of the tree are highlighted. So you see they are curves, simple curves. And these models are random. So there's each realization gives a sample of those objects, and we are mostly interested in what these curves are doing. So in this other picture, you see 2 colors, which is the spin up and down. And then between the colors, you can draw this kind of interfaces or domain walls or whatever you want to call them. And because we are in 2 dimensions, it's just curves in the plane. And they interact in some way. And we want to look at models which are critical. Maybe I didn't write it here. So they have a continuous phase transition. And in that context, we expect conformal invariance. So that's important, because what I want to see is conformal field theory. So I need a field theory with conformal invariance. And somehow this is also the most interesting case of these curves. So the other cases are a bit less, at least arguably less rich. So we focus on this one. And so conformal field theory for me is the Belavin-Polyakov-Zamolodchikov approach from the 80s, where they said how in 2 dimensions, the conformal symmetry has actually infinitely many generators. So there's an infinite dimensional Lie algebra, the Virasoro algebra, generating that symmetry. And using that, they derived a lot of properties that should hold. And in particular, some kind of algebra of operators. So these are these primary fields in the theory. And some kind of rules, how they interact if you fuse 2 things together. So we'll see it in action very soon. So there's the central charge, which is some parameter related to this, what physicists call anomaly, but I don't know what you want to call it. I was told to call it anomaly. It's just the central extension of that symmetry. It's a parameter for me. So for each parameter, I might have different models. So this upstairs picture will have central charge 1/2. And the downstairs picture has central charge -2. So it's some magic how they are determined. Okay. And what's important for us is that there are certain operators which are special. So people talk about singular vectors or null fields or degenerate fields. So this will appear also. And what's important for me is that from analytic point of view, I find some partial differential equations for correlations of those operators. And this we can work with mathematically. So it's a la Bellavin-Polycosm-logical. So it will come later. Don't worry about the buzzwords too much at the moment. But that's just the CFT content that I'm focusing on. So it's quite simple in terms of kind of algebraic content and some analysis. So it's maybe in a naive-minded way compared to many other formulations of conformal field theory. And I already said how we have these kind of interfaces clearly in the pictures. And because they are given by some underlying model, there's some interaction that they have. So for instance, in the downstairs thing, those highlighted ones, they cannot cross each other. So they cannot be like independently sampled, right? They are in this underlying model. And then we are interested in how the interaction is described and how it's related to this CFT content. Okay? And people in this business, so instead of somehow correlation functions, they talk about partition functions. Maybe because oftentimes how it arises is like in the top picture from some boundary disorders. So it's just some terminology that's common, but this is describing the interaction. And maybe there are some models you have heard of in your statistical physics or whatever courses. I listed here what I guess physicists would call quite trivial because these are free theories. But for me, they're not free because of the interaction of these interfaces. You see, I have some topological observables. They are non-local. They are very complicated. So somehow the underlying theory in many of these models is still somehow the free theory. So there's the free boson is one example. The last one is what people would say it's a symplectic fermion theory. So this is this picture. But then I have non-local observables there. So I don't even know if I can realize them just using the symplectic fermion. So maybe it's some kind of modification of that theory anyway. So what I think is that they are actually not free, but there's the underlying free theories and then some added interaction, but we don't quite understand it. So we try from the basics first. Okay. I guess what I'm gonna say is focusing on the Ising model because it's easiest to describe using these pictures. So that's the upstairs guy, and you might tell me it's the free fermion or something like that, or you could say it's the minimal model of such and such. But my observables are outside of that model. Okay, so far so good. Yeah.
What do you mean by topological events?
Yeah, so it's somehow, if you look at the picture, there are some kind of insertions here, which I will show soon. And the curve is growing from that insertion. And then I could ask what the curves are doing globally. It will come in a couple of slides a bit more carefully. But it means that I need to know somehow a lot of information from the whole system in order to decide if the event happened or not. So I cannot look locally. And topological because I look at some kind of connections. I think another slide illustrates it. Yeah. Let's see. So before that slide, I just made this cartoon of what kind of connections we want to draw, like in the initial stage. So this is maybe already some work during 10 or 15 years or something like that from this kind of probability community. So people were interested in these critical models in discrete lattices. So I'm going to work with the plane. It's very simple because we need some embedding and it's complicated in general. So plane is the easiest. So we lose the complications from the geometry. So you put some lattice model there, like your favorite pictures that I was showing. So in the scaling limit, where this size of the grid goes to 0, we expect some quantum field theory with the conformal symmetry if we are in the critical case. So that's the kind of physicist arrow that's, you could say, maybe clear because of renormalization group or whatever. So for mathematicians, it hasn't been very clear. So that's been something people worked on a long time. If you look at these curves, you get something that people term SLE. So it's called Schramm-Loeffler evolution. It's just names of some guys and then evolution. So what does it mean is that if you want to follow those interfaces in the pictures, so here's a tiny one, it's some random non-local object, it's a curve. And then we might be interested in what people call partition functions of those guys. And again, those things should be related to CFT. So there's some kind of triangle of relations that you could think about. And for me, maybe this triangle from those curves to the CFT has been the biggest puzzle, because the upstairs one is already what you kind of expect, right? And then how these interfaces arise, you just look at the picture. So the really mysterious part is over there. Okay. And yeah, so I think it soon Reiko's question will be answered. So before that, I formulated the conjecture, but I don't know how to formulate it because it's not so precise. But in any case, just to provoke you. So this is what physicists seem to be claiming in the 70s, 80s, or maybe even earlier, is that if you have a scale invariant model in the statistical physics world, which is a discrete world, and you take some kind of finer and finer grid, you get these pictures where the grid is kind of disappearing. You should see a field theory with conformal symmetry. But like I said, I don't know how to formulate it. So instead, I'm going to look at some kind of objects here and try to understand if they have a limit and if that limit matches something in CFT. And some things I could look at. So here is now the answer to the question. So the topological event is the green one. So what do I look at? So the easiest thing is to look at something with boundary, because then you can say that, okay, so inside there's some mess. There's this random model. And at the boundary, I put some constraint. So this is the model will come soon. So I have plus and minuses, up and down spin. And I freeze on the boundary on two sides here, just minuses. And on the other two, I put pluses. Pluses are black and minuses are purple here. And then, so those corners I call x2 and x1. So there's some points, right? And then I will always have some kind of domain wall or interface separating the plus and minus between the x1 and x2 because we're in the plane. So then I will always have this interface I can study if I freeze the boundary condition. Inside I have my random model. So it's easier to study if you have in every scale of the lattice, you always have the object to study. So that's one thing that. So kappa will be a parameter related to the central charge. It will come. Yeah, a good point. So this is terminology again. But the point is there's a curve. Of course, inside there's a lot of loops and stuff, but I don't know where they are. It's a bit harder. So we can analyze them too, but I want to forget that right now because what's useful for us is to understand what these curves are doing like in general. And it's good to know that it's going between two given points, right? So that's why I'm doing this constraint. Another thing I could ask if there's many curves. So down here, I have 4 points because the rectangle has 4 corners and not 2. So I put one color on the top and the same color on the bottom, and then the different color on the sides. And then I will actually have kind of a connection of either from top to bottom or from left to right, right? So the top to bottom would be green and the left to right would be white in this picture. And this I can detect by, again, following those weird curves and see where they end. So now there's a topological event, whether we have a top to bottom connection by the green color, or we have a left to right by the white color, right? So that's a well-defined event in my model, and I can ask about this probability, which is a number between 0 and 1, okay? It's quite simple question, but of course it's going to depend where these marked points are. So I decided they're in the corner. Yeah.
So what are these x3 and x4 points?
So I fix them. I decide that let's pick some points on the boundary. So my domain is this rectangle, and I do a model inside. And I decide, okay, let's fix this x1, x2, x3, x4 at those corners just for simplicity. And then let's impose that condition. And then, yeah, so things are going to depend on those points. And of course, they are some insertion of some operator or something like that.
So just to clarify again, it's the analog of what you were doing in that.
Yeah, so I'm doing more. So here I have, let me fix 2 points. I just decided they are those corners, so the picture looks nice, right? And then I decide here is minus spins, here is plus spins, inside is the random model with those. Yeah, so the points are fixed and the domain is somehow also fixed. But if you change the domain and the points, we have some conformal maps, right? So we can use the symmetry. Yeah. So it's a motivational picture. So let's make it more precise in the next couple of slides. But these are kind of objects I can define mathematically, and I can ask, okay, so how do they behave in the limit when this grid size goes to 0 in the critical models? And okay, so you could just look at correlations of things, but we will skip that one. So that would be more local. Okay, so let's forget about that. Let's see. So I wanted to give you an example model, which is the Ising, just to be clear that we understand what we are doing. So the Ising has those 2 colors, plus and minus, up or down. And you don't have to memorize any formula, but if you're familiar with them, so there's these spins, which are the plus or minus. Each vertex of the graph has 1 spin. So it's this color, right? And they interact in some given way. So there's this kind of Boltzmann measure. So nearest neighbor, x tilde y, means x is next to y in the graph, okay? So they are only interacting with the next door in this model, because you could do more general. So nearest neighbor, and then there's this capital T is the temperature, so 1 over T. And I'm having the ferromagnetic, so the sign goes like that. So what does it mean then? So it means that they are interacting, and in, let's see, low temperature, so the capital T is small, they all want to be somehow very similar. So here I put those constraints on that side, this purple color, and on the other side, the black color. I think it's obvious. You see what I put on the boundary. Inside, I sample randomly, and I see something. It's a bit cheating. I think there should be some tiny fluctuation here. But you see something completely ordered almost in this small temperature phase. In the high temperature phase over here, it seems like the different colors are not very much correlated. So we had some talk yesterday about, you look at the picture, do you expect correlation, right? And in the critical temperature, that was found by Marie Curie, looks like that. So it's somehow fractal. It's quite weird. You can actually see some scale invariance here, I guess also there. But it's quite different, right? So this is the phase transition for this model. And in the lab, how people can observe it is that Ising model is some kind of ferromagnetic material. So you can have it in room temperature when it's not usually magnetized. I guess you have to choose your material. So your physicist friends can tell more carefully. But when you have something that's still magnetized in room temperature, you can put a magnet and then it's attaching to the magnet, right? But then if you heat it, put some kind of heater below, then the temperature rises in this body, and at some point it becomes not magnetized. It's going to drop from the magnet. So you see abruptly that you go from somehow being magnetized or ordered to this disordered, and there's some unique, not time, but temperature where this happens. And this is the critical point. I think, yeah. So there's some universal constant, which is for the spin interaction. So there's some power scaling dimension of them. So you see here, there's a big correlation. It's like order 1. Here is exponentially decaying. So this is the correlation length. It's a bit small because the formulae are not meant for you to remember, but just if you already want to look at them. And here there's a polynomial decay. So what does it mean? X and Y are some points. I'm interested in how those spins are correlated when the distance is large. So I didn't write everything on the slide. And here it's a polynomial decay of far away spins, exponential decay, and somehow no decay. Yeah, and there are some, I forget, maybe this is 116 or 18, something like that. Yeah, so this you can calculate, and it relates to actually this eigenvalue of the Virasoro scaling operator. So these are very important numbers in general. Okay, so that's the phenomenon where you see scale invariance, and it's quite peculiar, but you can see it in these colored pictures. So you can forget about these sigmas because we can see it in the picture, right? And then what I was interested in is not really those spins as such, but how these interfaces behave. So then let's see. So this was the top arrow kind of, or something like that. So what is this interface now? So now the kappa appeared. So I did not write here the central charge in terms of kappa, but there's a formula. So kappa was used by Oded Schramm, who introduced this object in 1999. And then we've been using kappa all the time because somehow convention. Also, he died in a hiking accident, and we want to honor his memory. So we are keeping his choice for this parameter. I should have removed that. So that was for some percolation model. So yeah, so there's a formula relating the kappa and the C. Kappa will come soon, what it means. But for each parameter, you have a model of curves. And for the Ising model, yeah, it kind of looks like that if you forget about the colors. And then you can take a limit. And if you're very familiar with this, there are some bullet points. So I'm recycling some slide that was for the experts. So by the way, some Fields medals were given by this work. So it's not very easy to do. So I'm not trying to explain how these things are proven. But the claim is that in this Ising model, for example, if you look at that interface, so forget about those colors, take this, delta is the size of the grid. So maybe I should, yeah, here is this little grid. So it's delta times delta, because I want it to go to 0. And epsilon is normally used for something else. So delta go to 0, it becomes some continuum object. And the claim is that the limit exists as some space of measures because it's a random curve. But we can just look at the picture. So each realization has a limit. And it's something we understand, which has this acronym. So I want to tell you what it is, okay? And how it relates to CFT. Yeah.
The scaling limit, sorry, no.
This one?
Yeah, scaling limit on the both sides, SLE and the CFT, are they the same scaling? Do you
Yeah,
take
so
the
exactly,
delta?
yeah, this scaling limit is the same as that.
Okay.
Yeah, so it's like just the delta go to 0, which is the, yeah. And here I'm just looking at whatever you want to define in the CFT. So the top one is kind of matter of what kind of thing you understand as CFT. But the bottom one is I want to look at the interface, and then I look at that curve only. In the scaling limit, it becomes that kind of curve that I want to tell you about. And then I can relate to some stuff in CFT, namely a certain operator that people label phi12. So it's this degenerate field, which are very special in the classification of the primary fields in two-dimensional CFT. But the scaling limit is the same. So it's like do a discretization and then, yeah, somehow take it a continuum limit. So in particular, the volume is staying the same. So here I removed, but I have this volume, which is some kind of unit rectangle. So this curve is also living on that rectangle, right? So it's not the infinite volume limit. The volume is the same. It's the scaling limit where the scale becomes 0. So that's a crucial difference here. Okay. And let's see, how can I wanted to have some slide which looks a bit complicated, but then we come back to it. Because I want to point what is the CFT content in these curve models. And yeah, so here's the cartoon where you start seeing those interfaces. So I guess here I have several of them. You can always detect that in the boundary, I made some choices, right? With different, the color changing. And that's supposed to be some disorder happening there, right? And there was work by Cardy in the 80s, actually quite early, understanding the boundary phenomena, because he was very interested in statistical physics and its relation to CFT, and well, many things, right? But that was one thing he was interested in. And then he and Michel Bauer, Denis Bernard, and others, they came back to this in around 2000s because this SLE kappa curve was only introduced then. So physicists didn't understand what those curves really are. But what Cardy already said in the 80s is that this change of the boundary spin color is some disorder operator. And he even calculated what it should be. And he said, is this and this primary field? So for us, it's just a symbol, but he kind of knew precisely what it should be. And of course, this was in the physics level of rigor. So then we've been very puzzled, can we prove this in some way? Because this object is just an abstract object with some algebraic properties, while I'm having some kind of random probability measure here, right? So what do we know about this prediction of Cardy is that the bottom line, so now there's decoration formula, so it looks a bit awful, but the point is that if I take correlations of that object, maybe this guy here should have been the bracket with the correlation, to actually find a differential equation. So I will get back to this, but it's gonna be some not so horrible looking differential equation. So what I'd like to see is how these curves are related to those differential equations. So these are what Belavin, Polyakov, Zamolodchikov were deriving from the conformal symmetry. And in the middle here, I have something that's called the martingale. So let me explain what it is, because I think most people are not familiar with that.
Ask a quick
Yeah.
clarification. What is 1, 2, 5? 5, 1, 2?
Yeah, so this is what Cardy was calling this disorder operator. So it should be a primary field in a conformal field theory with special properties. After some slides, I will show what it should have. So it should be a degenerate field in the sense that it generates a Virasoro module because it's a primary field, and that Virasoro module is not irreducible. Okay, so I will get back to it. So it's a special one. Okay, so I'll come back to all of these things. But let's start from whatever I had. So you can also do fusion, but there's phi 1s. So if you're familiar already, but if you're not, just forget about that. So it looks like minimal model, but then the problem is there is not going to be a minimal model because they are non-local. Yeah, and that's the puzzle. So it goes outside, but it's the catch. These labels are the catch table. Yeah. So yeah, but it will come. If you bear with me. I was a bit worried that you get confused about the curve and not about the CFT content. So I have put the curve thing first. So here is just, again, what are we imagining is that we have this fixed volume thingy. And now I keep the color here, but I'm interested in this curve that's between the two. In this case, I have the 2 points, right? And so how can I describe it? So it was this thing that was introduced by Oded Schramm. And there's a lot of passwords here in case you are familiar. But what's important is that it's conformally invariant in the sense that I can send this rectangle into the half plane. And now the curve can start from 0, let's say. So let's say that corner went to 0 and the other corner went to infinity. It's convenient for the formulas like that. And then I could start growing from here. It means I'm just starting to explore this interface from the picture, right? And I take some kind of, each lattice step is maybe one time step. But then in the limit, there's no lattice steps, right? So then the time becomes a continuous time. So there's at time t, I'm somewhere, right? And then I go on. And what was discovered actually is that because of this conformal invariance that we want to impose, there's not so many choices what this curve can be. So namely, so if it's a simple curve like that, at time t, I discovered some slit. So the complement of the slit, half plane minus that, it's a simply connected shape. So I have a uniformizing map, a conformal map that I call GT because it depends on the time index. That's removing, it's like unzipping. You know, when you explore from here, you like making a zipper, it's just winding around. So if you undo it, you open your zipper. So you should imagine some kind of map that this slit is going to be mapped away. And this, at time t, where the walker is standing, it's going to go to some point on the real line. So I go back to the half plane. And what I need to follow is where is this tip going, right? And then the rest is mapped somewhere. So if all time I know where the tip is going in this map, it's a bijection, so I can go backward, so I get everything, right? So what was the discovery of Schramm that was actually basic complex analysis fact, like 100 years earlier, was that this two-dimensional curve I can actually understand as one-dimensional object, because I only need to track that one point where the curve is at the given time. If I know those conformal uniformizing maps, and there's some equation for them. So don't worry the equation too much. It's not very complicated to derive, but maybe it's beyond of what I want to say. So it's just something you can solve if you know this where the tip is going. And so I wrote here the kappa now appears and B. So what is B? So I have a random thing. And what's the favorite random object for most people doing in the continuum stochastic processes is Brownian motion. So in the real line. So real line is the boundary, right? And then I put some speed, which is this kappa, because the winding, how much the curve is fractal, is depending on how much somehow this tip is moving when the time goes on, right? So the thing was that in order to describe these models, you don't have much choice. So you have to describe this tip when the curve is growing by one-dimensional Brownian motion. And all you have left with is some parameter. So you get like one parameter family. So there's another keyword, which is a Markov property that let me skip because it's not important for us. But it's saying something about it doesn't matter, you know, how, in which order you grow. Oh, okay. Yeah.
Thank you. I wanted to ask you something about that. What if you drop that assumption? Then do you have anything, or is it too difficult to tackle?
So then you have to put some other, like you can make a choice, essentially what this guy here is, and then you plug it into the equation and you can solve it, but then you have to ask what you get. And it's very complicated. So you could relax some things and get, for instance, this could be a Levy process, but then it's jumping, so it's not going to be what I want. You could have something that's not Markovian. So this Markovian is just that it didn't really matter, like, you know, I want to grow there, but then if I stop and start growing again, it looks kind of similar. So it's something like that. But yeah, so there's a whole theory, we call it Loevner theory. So Loevner was this complex analyst in 1920s who was actually working with this stuff because he wanted to solve some big conjectures in analysis. And well, he didn't solve them, but they were solved later by his technique. So it was very important actually. But for us, it's very convenient that it's known and you can have that formalism. And because we want something very special, which is conformal invariant things with this kind of Markovianity, we don't have much choice. But yeah, of course, you can generate all kinds of things. And it's actually a nightmare then to figure out what they are. Yeah. Yeah,
it can't be
question.
completely Markov because you know you must end up in the top corner. How is that?
Yeah, so the thing is that the process here is just in the boundary. And then for each time I need to send it back by this map. So there's some non-trivial information in this map. And actually you have to prove, so you can prove that when time goes to infinity, so this thing is gonna grow to infinity. So yeah, so it is Markovian, but the point is that when time goes to infinity, actually Brownian motion is really badly behaved, right? So we don't really like it very much. But what is happening here is that you can take some limit and you end up in the correct place. So actually, you're right that if I don't want to end up infinity, but to some other point, like in the rectangle, I could go there, and then it's a bit more complicated. Indeed, I need to make this target point somehow attracting, and it means introducing a drift. So if you're a probabilist. And then, so it's a Brownian motion with drift. So it's still Markovian, but you keep track of this other point. I was hiding it by making it infinity, and then it doesn't move somehow. I don't know if it helped. But these maps here are normalized in such a way that infinity is fixed.
Thank
Yeah.
you. I'll talk to you
Yeah.
later. Yeah, thanks.
Yeah, it's very non-trivial. And also, actually, it shouldn't matter which way I go. Like I could start from the other corner, right? And it was a very big theorem to show that you can actually start in both ways. Like, it's very bizarre how such a simple thing can be so difficult to analyze rigorously. That, yeah, it doesn't matter which corner I send to 0 and which corner to infinity, because the time evolution is like causal. There's one direction of time, but here it shouldn't matter, right? But so what the nice thing about this description was that we could concretely construct these guys and, you know, make computer simulation, etc., in a manner where it's evolving in time. So that's why it's called evolution. Yeah. And the only input of randomness is the Brownian motion. So the upshot here was that it's kind of something we can understand quite well after some work. So if you go to the details, it's a 1 semester course. So unfortunately, this object is very nasty to define rigorously. But if you believe the heuristics, which kind of makes sense, you can work with it. So you don't have to go through all the technical details of how to make it precise.
Just needs to be continuous.
Yeah, so I
There's
want it to
no-
be a continuous curve because from the picture, you know, I expect that. Yeah.
Okay, so you could in principle just stop it at some finite time, and
Yes.
it will be a purely Markovian process. And
yeah, so-
the last step, if you like, then just attaching
Like
the
a
last
next
leg.
step. Yeah, so the Markovian is in the downstairs, right? And then there's still this map. So the curve is not really Markovian because it has to feel the surroundings. That's the point that, yeah, it's like these are non-local. And that's the whole difficulty if you're in the 2D picture. And that's the idea that you go to one-dimensional model and there you're Markovian. But then you introduce back the 2D shape by those conform maps that, yeah, so somehow you cannot really, so here, of course, it knows where the past was, right? So that's it's a little bit puzzling to think about the Markovianity. Yeah, but I think from these pictures is easier because if you imagine how it was arising, I put this boundary, one color on two sides, one color, the other color on the other two sides. I start from some favorite corner where the color change. I explore a little bit, maybe I explore until there. So the left side of the curve is now pink and the right side is black. I could think about it as a slit rectangle, which is still some domain. It's a bit weird, right? But then the left side of the curve is part of the boundary and the right side as well. So now here, when I'm sitting, it's a similar starting point where the colors change. So the boundary condition is the same. So somehow it's Markovian in the sense that if you remember which domain you're at, then the rest looks similar. And maybe one way to justify why these interactions of these curves are called partition function is that it's really the boundary condition in those models that introduces this curve. And the Markovinity wasn't easy to see, but somehow Schramm understood that you can go to this 1D and then this boundary condition effect actually becomes something like that. Yeah. But okay, so the upshot is that people can understand these guys and you can generate them by some equation you want. And there's this parameter, which is kind of telling how wiggly we are. I think here is an illustration of what it's doing. So the parameter here is higher, you see it's winding more and more. It looks it's almost touching. So actually, if the parameter is very high, it becomes more complicated. So let's maybe not worry about it too much. So these pictures are still, this is not touching, but it's going very close to itself. It's very fractal, right? And here the parameter is 1/2. If the parameter is 0, it just becomes the straight line because there's no speed, right? The Brownian motion is just in the same place all the time. And there you actually get some kind of hyperbolic geodesics. So there's some relation to geometry here that's quite interesting, because the evolution here generates some kind of deformation of the domain, right? But the point is that the parameter that we call kappa is just telling how much the curve is kind of turning around. And it was really how fast this image of the tip is moving. So then you can pick, even with some simulation, if you have a model, you can try to see how windy this curve is. So I haven't had the SLE with parameter 3, which would be Ising model. So this guy would have parameter 3. So maybe you don't see it from the picture, but you can prove it. Okay, so that's the curves. And yeah, here is what I was kind of trying to say. What do we then, how do you see the interaction of the curve with anything else? So maybe with other curves or whatever. So one way to think about it, so if you're geometry minded, I put this cartoon that somehow helped me to understand. So now I put the half plane, I reflect it, because some people don't like CFT with boundary, but you could do the double somehow, and then you get the Riemann sphere. So now this one is actually the Riemann sphere, right? And infinity is some kind of nice point. So here is more like a sphere. And then this map, that's the zipper map. It's doing, it's a little bit small, but the initial piece is flattened out. I don't know if you can see the colors. And then this dashed thing is the future. And it's hand drawn, so it's supposed to be symmetric. So you can somehow see it as deformation. So here somehow how the Riemann sphere is deformed by this curve. And then these crosses are maybe some other points that I want to observe from. And of course, they are also moving in this evolution. And then I could try to ask how do they feel this evolution of the curve? So that's one way to kind of understand how the interaction is coming if you may be more geometry minded. And so therefore, I was having this decoration, lot of functions where, so now the WT, if I go back, it's supposed to be this guy. So it's where the curve is at the moment. And then there are some other variables, so GT of Z1, etc. So Z are those points, and then I'm interested in how they move. I might be interested in some function of all of those points and where the curve is growing. Okay. And then there's some prefactor that might look familiar if you know CFT. So there are derivatives of the map to those scaling dimension powers. So previously it was beta, but now it's called delta, and there's maybe the conjugate variable, right? And then I was claiming in the previous slide that this guy, when the time goes on, is something people call Martingale. And that Martingale gives us differential equations that actually then gets access to the CFT. So remember that there was this special field that I'm coming to, whose correlations satisfy differential equations. And I'm trying to say that from probability, we get the same differential equation. So then we can prove they're connected in this way, and we can prove some classification results that they have to be somehow matching in what you might expect. So you need to go from two directions. And Martingale theory is what probabilists start from. But if you CFT minded, you probably like, I don't want to talk about Martingales. So what is the point here is just that you follow the time evolution and you have some points or some other places where you want to look at the interaction from. And then what will happen is that you have some function of all that data, and maybe it transforms in some given way under that evolution because it's related to CFT essentially. And that thing is somehow nicely behaved. So that was the trying to just say why I was writing this line over here. So this was mainly if you already heard about it a little bit, maybe it helps. So what will happen is that that function is going to be correlation function of those mysterious fields. Okay. So that was the kind of trying to explain what this conjecture, how you could try to formulate it, because I don't know how to formulate it. Like, yeah, anything is described by CFT. Well, I don't know. How about even these curves? So I don't even know that so well, but now we start to understand it in terms of this analysis, okay? And it's really, you explore and you kind of ask how is the other things feeling, how the curve is exploring. Okay, so before I tell you about the CFT field, what's that? Okay. Ooh. Ah. Okay. Okay. Yeah, I thought there was 50 minutes, but anyway, so let's see, how should I? So I wanted to give you a more concrete way to understand that function. So maybe I can reveal it. So I was calling it Z. Somehow the font has changed. But if you're interested in the picture with those curves, right? And I should have put the points again here, x1, x2, etc. But it's a bit hard to put them in the slide. So those points are where the disorders are sitting. And then I could ask how, so I was describing how we understand one curve in quite detail. So now if we have many of them, so we cannot then just individually grow them, right? We need the interaction information. That's the difficult bit. And one way to understanding that I think is concrete is that if I have many curves, then they could connect in different ways. So this label alpha here means how does this picture look like? So maybe I should draw a simpler one. So we had this green picture earlier with like top and bottom being green and these two being white. And then I could ask if there was a green crossing like that, or maybe a white crossing like that. And how do I detect them is I have a pair of curves, right? So here the curves connect in this way, while here they connect in the other way. So there's only two ways in this case. In that picture, there's more ways, right? And the probability of each of them is something that I can try to ask. It's a very concrete question. And this slide that has a complicated looking theorem is just saying that that function that we saw earlier that wants to be correlation function of these mysterious fields that Cardy was talking about. You can say that there's a family of them and they are labeling these probabilities somehow. So this alpha label is one of those pictures. So maybe yeah, here is like alpha. I have a function associated to each alpha, and here you see the non-locality. Like I really need to know how the connection goes, and then I can form this function. And of course, it also depends on the shape and all those points and the parameter. And the key point is that it's matching with that correlation function of those fields that Cardy was talking about, and it's giving us the interaction somehow. So there's a lot of keywords here. So we can get conformal invariance and the differential equations that kind of identify this mysterious field. We can prove some other things. So here actually, yeah, it's a logarithmic CFT, so it's definitely not a minimal model. So it's something very mysterious. Yeah, and maybe now I don't have the time anymore. But maybe I can show how the correlation function of this one looks like so that we can just relate. So the moral was what Cardy was telling us. He's calling them boundary condition changing operators. And there's more general ones also. And it should have this scaling dimension in the catch table. And okay, so I reveal quite quickly, sorry about all the formulas, but if you're familiar, it will help. If you're not, I'm just pointing to the things. So what do we have in the conformal field theory? We have conformal symmetry, right? It's encoded in a Lie algebra. That's the Virasoro. So it's generated by these capital L's and then some central element with some commutation relation, right? So what is the point is that the fields in the theory, they carry representation of that symmetry. So then in particular, what people talk about is primary field, which is this phi thing. They generate modules of that algebra. I guess I was calling it M of phi by acting by that symmetry. And then I could ask if that module, if it's irreducible or what is the structure of that. And often I think physicists assume it's irreducible, but you have to prove it if you have a given model, right? So in our model, it's gonna be irreducible. But then you have to figure out which are the irreducible modules, right? And they are labeled by these weights, which is now h. Sometimes it's delta. I think delta is like 2 times h. So it's the eigenvalue of the L0 operator. That's the scaling operator. So that's the scaling dimension. People call it weight. Like in the theory of Lie algebras, there's highest weight representations, right? It's some number. And then there's the central charge that we already, so now is the formula here. So it's related to this kappa guy. So that we kind of fix, and then we're interested in which kind of conformal weights we would expect for those disorder operators. And that's what Cardy was figuring out. And that's what we can prove. And they belong to this, this here. So here's a label R and S. So for us, it was 1 and 2. And it's some explicit formula, which people call it a catch table. It was a result in the 80s that, okay, so how does it go? Is that this module related to the primary field. So we actually will see it's a irreducible module, but for those special weights, you have to see that it's a quotient of something. So if you do the usual Verma module, so if you're familiar with Lie algebras, there's this Verma module, which is just take all the algebra acting your vacuum and you get somehow a lot of stuff, and maybe it's not irreducible. So there might be some quotient, which is capital N here. And you take the biggest, submodule, and that's actually this M then. And if you quotient something out, it means you put something to 0, right? So that's the point, that for the special conformal weights, for the special fields, you put something to 0. And what does it mean for the correlation function? This is the last one I'm showing, is that the correlation function where that field is here, so that's one of the special ones, and these are some other ones, it doesn't matter. There's a differential operator that's horrendous, but for us it wasn't so bad. It was in the earlier picture, right? So it's differential operator is killing those correlation functions. So that's equation I can try to verify, and I can try to analyze all solutions to it. And the upshot from the previous discussion was that we can actually do that, and it's exactly the same as we see here. Okay. So that was it was very quick. So the labeling 1, 2 is just the R and S. Yeah, it's the textbook stuff in CFT. Okay, I should stop. Thanks.
Yeah, looks like there are a couple of questions, so let's take that.
Thank you. So how many of the known CFTs can you, for how many of the known CFTs can you find a critical lattice model? Find a CFT?
From these models?
Yeah.
So the issue is that I think none of them are really known, because they have these weird features that you can find these differential equations. But then if you do fusion, maybe I just put the picture here, is that if you have many curves next to each other somehow, if you fuse them together, usually what you expect is something like higher in this catch labeling. And maybe it should truncate at some point if it's minimal model. I don't know if you're familiar with this. But what we see is that it somehow never truncates. You can have arbitrarily many. So it's countable, but infinitely many primary fields. And sometimes you get logarithms. So then it's weird. So to my understanding, there are people in statistical physics and trying to study this, like Hubert Saleur, for example, to understand the content of these theories. So somehow the answer is that this is some CFT that's not completely known, in my opinion. Yeah.
Anybody else?
Thank you very much for your talk. So you work in 2 dimensions.
Yes.
Is there anything one can say beyond that?
Beyond 2 dimension. So of course this conformal map description fails, right? So we have this, maybe it's here. So I cannot do that, right? I can define those models. Ising model makes sense. Percolation makes sense. Random walks make sense. But then how to describe those interfaces? So for instance, in the Ising model in 3 dimension, the interface is actually some 2-dimensional, like codimension 1 object. And there's very little understood at criticality about them. So phase transitions people have understood, and some features in some models. For instance, these models involving spanning trees, there's some kind of understanding that there's some limiting object, but description is not very, yeah. So there's some work, but not by me.
You use complex analysis
Yeah,
very
very
strongly,
much,
and
yeah.
that's very much embedded in
Exactly.
the two-dimension. Yes,
Yes.
but there is higher dimension, higher parameter complex analysis.
So this actually already is, if you have many of those marked points, like in one of these cartoons, it's gonna be, oh my, a Riemann sphere with punctures. And then if the punctures are moving, you actually have several complex variables. But it's true that then if you want to go to higher dimension, I guess if you have some, yeah, I don't know, like even if you have an even dimension, because what do you do? Like if you project onto some two-dimensional, maybe you can say that those projections are described by this, possibly. But it's really, the other thing is that you don't have the infinite dimensional conformal symmetry in CFT. So it's really very different. Yeah.
Any other question? If not, let's thank her.